Now, in the second session of the today's lecture, we will learn about the Amdahl's law. Now, according to the Amdahl's, it states that if f be a fraction of operations in a computation that must be performed sequentially, where f lies between 0 and 1, the maximum speedup s, which can be achieved by a parallel computer with p number of processors performing the same computation, is given by s is less equal to 1 by f plus 1 minus f by p, where f is the fraction of the computation, p represents the number of processor, and s is the speed up. So what we have, what Amdahl's law states that if f is the fraction of operations that are performed sequentially, then the maximum speedup that can be achieved by a parallel computer with p processor is given by 1 by f plus 1 minus f by p. Now let's see some numerical problem based on the Amdahl's law, where we will find out the speedup. Also, if the speedup is given, how we will find out the number of processor. Now, if we will see the maximum speedup according to the Amdahl's, what it states that the if f is the fraction of operations that are performed sequentially, then the maximum speedup can be achieved using a multiprocessor. So here, if f is the fraction of operations that are performed in a serial section, and 1 minus f is a fraction of operations that are performed in a parallel environment, then the speedup is given by 1 by f plus 1 minus f by p. This is the representation of the Amdahl's law. Now, let's see the numerical problem based on the Amdahl's law. The question is, if 95% of the program execution time occurs inside a loop that can be executed in parallel, what is the maximum speedup we would expect from a parallel version of the program executing on 8 CPUs? So here, what we can see that what's given in the question, that the fraction of the program that are executed in parallel is your 95%. So what will be the fraction which are executed in sequential is 1 minus 95%. So you can find out it will be your, so what will be your fraction of operations that are executed sequentially is your 0.05, and there are 8 number of CPUs, or you can say that the processor. So the speedup will be given by 1 by f plus 1 minus f by p. So here the fraction of operations that are performed sequentially will be 0.05, and there are 8 number of processors. So the maximum speedup that can be achieved is 5.9. So in this way we can solve some other problem also. If the fraction of sequential uh, program execution time is given, then also you can find out the maximum speedup. Let's see some one another problem. Here it is written that 5% of the parallel program execution time is spent within inherently sequential code. The maximum speedup that can be achieved by this program regardless of how many processes. Here we have to find out the maximum number of processes that can be used to get the maximum speedup. And here it is written that 5% of the programs are executed sequentially. So here how we can find out the processor? We will write down the Amadel's law formula, 1 by f plus 1 minus f by p, and using that formula you can find out the number of processor. So in this module, or in the first module of the parallel computing, we have learned that what is parallel computing, what are the advantages of parallel computing, and the application areas of parallel computing. There are some important terminology associated with the parallel computing, like what is supercomputer, what is throughput, what is data parallel approach, what is control parallel approach. And then we have seen one control parallel approach, that is a pipelining, and how pipelining is different from a data parallel approach, and or how it is different from the sequential approach. Then we have also learned that if we take any algorithm, and if we will execute the same algorithm using a control parallel approach or using a data parallel approach, how the things will go on. And finally we have learned about the Amadel's law. Thank you.